Okay, in this lecture, we're going to study normal stresses in what are called composite beams. Okay, and what we mean by composite is we have a beam, let's say, and where part of it is going to be one material 1, and then another part is going to be a different material, okay? And so this will have a Young's modulus, let's say E1, and then a different Young's modulus, E2. Okay, and so let's just go through our 3 steps where we look at kinematics, or the geometry of the problem. And then we'll look at constitutive behavior and how it relates to stresses. And then we'll do equilibrium to pull in the external force, to external moments in this case. Okay, so number 1, if we look at the geometry of the problem, remember, strain, epsilon x, doesn't depend on the material. So it stays exactly the same. So we're done. Just we use the exact same idea of strain as we had before. Okay, maybe I'll put another graph here. Okay, so here we've got, let's say, and another thing to keep in mind, which I should have mentioned at the beginning, is that when you have a composite beam, the neutral axis may not coincide with the centroid. Okay, so the centroid of a beam of a rectangular cross-section, this would be the centroid C, but depending on the material properties, the neutral axis is not going to be at the centroid. It's going to be at the location where the normal stresses are 0. Okay, so that's a little complication. So let's say we've got, let's say this is the neutral axis. Okay, and let's say this is E1 material, right, from here up, right, this, and then let's say from here down is E2 material, okay. Now if we look at, let's say we're going to look at sigma x, okay, because now we're going to be studying the constitutive behavior, stress-strain behavior really, constitutive. Okay. We know that the stress in material 1 is just E1 epsilon x, and the stress in material 2 is E2 epsilon x. But let's plot these guys, okay? So we know that the normal stress is 0 through the neutral axis, and if the loading on this beam is on the top, that this is going to be tension down here. Okay, and that's considered to be a positive normal stress, so we have some value sigma x equal to E1 epsilon x here at the bottom. We know that it goes through 0, and then we also know that it's going to be some value, let's, another sigma, this is going to be another value, these are going to be connected by a straight line, although that's not very straight. Okay. Now, if we look at the first material, okay, let's say, for example, that E1 is greater than E2, then we know that sigma x2 at this location, at the change in the materials, it's going to be something less than this value right here. Okay, maybe it starts here, and then it's going to increase to some final negative compressive value. This is sigma x1, sigma x2, E2 epsilon x. And we're going to go ahead and do that. Okay, there you go. So you can see that there's a jump, right? There's a discontinuity, a discontinuity in the stress, and you expect that because there's a jump in material properties. And so this is common to composite beams. Okay. All right, so this is the stress strain behavior. We just have to recognize that it's different in the different materials. Let's go to the last step now, which is equilibrium. So if we look at equilibrium, okay, so we're going to look at equilibrium. The first thing we want to do before we move any further is let's go ahead and identify the neutral axis, because up to now it's been left unspecified other than to say that it doesn't necessarily coincide with the centroid of the cross-section. And so we know that the property of the neutral axis is that it's the location where the resultant axial force is 0. So if we look at the axial force coming from stress 1, and we look at the axial force coming from stress 2, that better be equal to 0 at the neutral axis. Okay, so let's go ahead and plug in our expressions for stress, just to kind of simplify this down. Okay, and we end up with E1, after canceling out kappa because it's constant, y dA plus E2 A2 y dA. That better be equal to 0. Okay. And this, of course, is just Q, first moment of area. First moment of area, second moment of area. So we have E1 Q1 plus E2 Q2 better be equal to 0. So let's look at a little example. See if we can see how this works. If we have a cross section, let's say something like this, okay, and we've got, let's say the neutral axis is at some location. The neutral axis is at some distance h1 from the top of the beam. This is what we have to determine. This is what we don't know. Okay. Let's say this is, I don't know, 6 inches, and this is 0.5 inches, and then this is 4 inches. Okay, let's go ahead and write Q1 now, in this case, as a function of H1, and Q2 as a function of H2, right? Okay, so if we look at A1 y dA, that's going to be equal to the area of 1 times the distance to the centroid from the neutral axis, which in this case is simply, let's see, 4 times 6 h1 minus 3, and then a2 y dA is, let's see, a2 y2 bar, which is, let's see, 4 times 1/2 times negative 6.25 minus h1. Okay, great. So this is Q1. This is Q2. So we can take this expression here, plug it in there. We can take this expression here, plug it in there, and then we just solve for h1. So that's one way to determine the neutral axis. Okay, so now that we have that, let's go back to equilibrium. Okay, so let's go back to to equilibrium. We have the moments. All of the external moments better be balanced out by the negative. This is from previous lectures. We've been through this same calculation. And then we can break that integral up into area 1 with sigma x1 y dA minus area 2 sigma x2 y dA. Okay, and then plug in our quantities. We have kappa E1 are constants, so they come out of the integral A1 y squared dA plus kappa E2 A2 y squared dA, which then becomes kappa E1, then the moment of inertia of I1 plus E2 I2. Okay, now let's divide through, so we get a moment curvature relationship, means that kappa is equal to m over EI I1 plus E2 I2. Okay, so this is called a moment curvature. It's kind of an intermediate calculation on our way towards our final calculation here. Okay, so now we know that, for example, sigma x1 is equal to E1 epsilon x, which is equal to E1 minus kappa gamma, minus kappa y. And now we have kappa, so we can replace kappa with our moment curvature relationship, giving us minus E1 y m over this thing here. Okay, and then we can do the same for sigma x2. All right, so that is a way to handle composite beams. You just notice that it's pretty much analogous to what we did for beams of a single material, except that we have a distribution of stresses that now depends on the distribution of material. There's one other approach that we want to talk about just because sometimes it's convenient. It's called the transformed section method. And the question that it's trying to answer is, if I have a beam of two different materials, okay, call this E1, E2. Maybe the neutral axis is down here somewhere, all right, where this is B2. Does there exist a transformation? Can I do a transformation where I can think of an analogous beam now where everything is E1? Right, so this now is E1, and then this is some factor of B2. Okay, so that's what I want to try and do, because now I've taken a beam problem where I have change in material and transformed it now into a section where it's all one material. See, both are E1, but I've changed the area of material. And so you want to be able to do that because, like, for example, if, let's say E2, just for an example, let's say E2 is greater than E1. So E2 is stiffer. So if we set N equal to E2 over E1, that gives us some ratio of stiffness. And so conceptually what you should see is that if this is really stiff, and you want to change it into a softer material, right? This is softer. Then for it to carry the same amount of load, axial load, which is distributed over area, you're going to need more area. Okay. And the amount of area more that you need is embedded in this factor n, which is just ratio of the stiffnesses. Okay. All right, so that's good. So what we're going to do then is, for this particular problem, the way that you want to think about this problem is you want to do a transformation. You want to perform a transform such that the neutral axis is located in the same place, right? So the distribution of stresses from bottom to top should be the same. And the moment resisting capacity is the same. So it can carry the same amount of load. Okay, so if you recall from before, the neutral axis, the equation that expresses that statement is this one here. So those forces better be equal to 0 at the neutral axis. Okay, we can divide through, okay, like this. Okay, so that's 1, and then we take our n here, plug it in there, okay, which tells us that a1 y dA is equal to, let's bring the n inside of the integral y n dA. And notice here what's happened is in order for this equation to be, in order for these two equations to be equivalent, you need to scale the area dA by n. But you need to scale it in the horizontal direction. Okay, horizontal direction, meaning that it gets bigger, right? Because if you made this long and skinny, it would change the location of the neutral axis. Okay? All right, so if you do that, then you now can compute the new stresses. Sigma x1 is just minus my now over I of the transformed section, inertia of transformed geometry. Okay, and sigma x2 to m minus my over I times n. Okay. So this n here, this n is scaling it down. Okay. Great. And so what you can see here is if you have the same moment of inertia, right? The material that had higher stiffness, let's say n is greater than 1, okay, that would mean that n is greater than 1. That implies that E2 is greater than E2 and then E1, okay, which means that the stress should go up, right? Like if you got rid of n, and just used the transform cross-section of the moment of inertia for the transform cross-section, the stress would be too low, right? It needs to be scaled up because the stiffness is actually higher. That's what that n is saying.